Well, it does not appear that any students are coming to this. It's 2 minutes after. I'm thinking about just doing a discussion of star motion and of Kirchoff laws and explaining that for my astronomy students. I think they need the most help, even though this was for all my physics classes as well as my astronomy classes. So let me go ahead and start doing that. What I'm going to do is I'm going to share my screen, and I'm going to share it with my my iPad screen with you. And from that, I'm going to draw a picture of the celestial sphere and help you figure out how you can use that to understand star motion. So let's do that. First off, I'm going to draw the Earth as a circle, and it's going to be way bigger than reasonable, but luckily this program will actually correct my circles. And what I'm going to do is I'm going to show it with us here being here in northeastern North Carolina / southeastern Virginia. And I'm going to draw the equator across it. So that's the equator. And then we'll choose another color and draw the rotation axis, which I'll use green for. Okay. So I'll write down here that red, whoa, doing some crazy stuff because it's trying to interpret my letters as some kind of symbols. Say red is the Earth's equator. And I'll say green is the rotation axis. Okay. So what we do with the celestial sphere is we imagine a similar sphere whose center happens to be the same as the sphere, as the Earth. And in that scenario, though, the radius of the celestial sphere is like infinitely large compared to the planet. So we're really overdoing the planet. I'm going to also draw a line that is vertical for us. And like I said, northeastern North Carolina and southeastern Virginia, that's a vertical line. Okay, and in fact, that points to directly overhead, which I think you all know is your zenith. And of course, if you followed it downward, it would point directly down to your nadir, N-A-D-I-R. And zenith, of course, is the point directly over your head. Hopefully you already learned that. Now let's try to draw the celestial sphere, which I think I might make into a nice, pretty yellow. No, yellow kind of stinks. That's a favorite color. Let's make it a gray. Okay. So what I'm going to do is I'm going to draw a circle. So I'm going to attempt to be centered on the Earth. And that's not too bad. I would actually like to move it just a tad. Let's see if I can do that. Evidently, it does not want me to do that. Oh, yep, it does. Okay. All right, so that's the circle, and it's about centered on it. That's supposed to be the celestial sphere. So just remember in this drawing, the Earth is infinitesimally small. We're just drawing it big so we can see it. I'm going to draw a person on top because that's where we actually stand. Okay, and obviously the person is way too large as well, but there's our person. The important point about this is if I continue drawing this rotational axis, it'll go through a very specific spot on the celestial sphere. And This spot right here is called the North Celestial Pole. And this spot right here is called the South Celestial Pole. And then, of course, directly on top, we're not drawing this in 3D, we're looking at it flat on, but directly on top of the Earth's equator is the celestial equator. Okay. And if you imagine that we're, of course, in this particular part of the United States, we know, for instance, that the east coast of the United States is right about here, and Florida is down here, say, and here's South America down here, so on and so forth. And this is like, say, the west coast of the United States, Canada, so on and so forth. So what we know is the Earth rotates this way. So to represent that, what we got to imagine is that instead of knowing the Earth is rotating, we pretend sort of like the Earth is sitting perfectly still, and the celestial sphere, this big gray circle, is rotating the opposite direction, and that should give us the same effect. And that means the celestial equator, or excuse me, the celestial sphere should actually rotate this way. So that's the celestial sphere's rotation. Now, for us, the our horizon is, of course, since we know this black line going up is actually pointing to our zenith. And our nadir, then we know that our equator should be perpendicular to that, or excuse me, our horizon should be perpendicular to that. So this is our horizon. But remember, the Earth is really small. It's nowhere near as big as it suggests. So I can't, I can't even see when I'm on top of the Earth right here. I can't even see past the edge of the Earth to see the equator. So we're actually imagining this thing going infinitesimally small, the Earth going infinitesimally small, and everything else staying the same. And we're standing right there. Now, since this point right here is directly below the North Celestial Sphere, this is our north point. Which doesn't sound that familiar. Of course, if we go to the opposite side, this would be our south point. And of course, the back of the sphere, right behind the center here, is the east point, and the front of the sphere, right in front of us, on this side of the sphere, closest to us, is the east point. Let me double check that. No, I said that backwards. The back of the sphere is the east point. I think I said it backwards. The back of the sphere is the east point, and the front of the sphere is the west point. So if I made this sort of circular, or at least elliptical, to show the three-dimensionality of it, it would look like this. And what we'd say is this point over here is our east point. And again, that doesn't sound very familiar, but this point over here does sound familiar. This is called our West Point. And you've probably heard of, the West Point University, which is really one of our military universities. But anyways, that's how we look at this. So it obviously on this this horizon that we see, anything below it is not being seen by us because the Earth is blocking us, and anything above it we can see until it rotates in or out of it. Now we're picturing the Earth rotating this way. The big blue circle that goes down and to the left, that's the direction that the celestial sphere is rotating, to represent the Earth rotating, of course, exactly the opposite way. So if you actually were to turn and look towards the north, what you would see is stars would go around the North Celestial Pole, which is very close to Polaris. Stars would go around that in a counterclockwise fashion. So a star over here east of the North Star would go up and go above the North Star and then come back down west of the North Star and then be directly below the North Star and so on and so forth. So we see a counterclockwise circle. If we looked over here, the center of the circle, of course, we'd see a circle as well here. But in this case, an object might rise here, go due south of us at its highest point, and then set over here like that. And that, of course, is, if we're looking to the south, that is, oh, I did it wrong way, sorry about that. If we look at it this way, because the Earth is, the celestial sphere is rotating this way, we will see a clockwise circle. Okay. So now let's see if we can put that together. And again, this isn't, this drawing that I just made, for instance, isn't the best. Let me try to draw that a little better. See, I was trying to show the three-dimensionality without changing the celestial sphere, but I couldn't exactly do that very well. So let's try it again. I'm gonna go back to my gray, see if I can fill in this little mark right here, make that look like a celestial sphere again. Okay. So now what we'll do, it'll actually look quite odd, but if I imagine an object that's actually rising north of or east of north, I should say, then what I'd see is this object might be, for instance, directly below Polaris, or it might rise, let's say, right here. If that's the case, then what we'd see is it would rise, be directly south of us at its highest point, and come back down here. And if we saw something that went up here, we would see that it would rise, come around this way, and go like this. And again, if we saw something right here, it would rise, and this is the part that's hard to draw, and it would come back down here. So in this way, we see that this is counterclockwise. Now we can understand a lot of things. So for instance, we see that something rising, let's say due east, for instance, is going to go up, reaches due south of here, and then land somewhere back here. In other words, the distance between, well, actually, that one should technically go all the way to the south point, to the west point, but I drew it not quite perfect. So we can see that things, when we look to the south, appear to go in clockwise circles with the center of the circle down below our horizon. And if we look to the north, the center of the circle is the North Celestial Pole, which is very close to Polaris, and it goes in a clockwise fashion. So I can design that by looking at our horizon and drawing that instead. So let me see if I can get that shown. I want to flip to the next page. And what we're going to do is we're going to draw the horizon looking due north. And that did not come out well. I'm going to use my cheater thing. Make a nice straight line. Okay, now due north is right in the center. And then, of course, if we're on our coast here in Virginia or North Carolina, if we're on our coast, we know when we look north, say towards Maryland or towards Virginia, if you're in North Carolina, we know that the ocean will be on our right. And of course, the ocean is the East Coast, so that's our east. And we know that the sand dunes in North Carolina or the businesses in Virginia or Maryland will be on our left side, and that is west. So if we look up, it turns out a certain number of degrees, and that number of degrees happens to be your latitude. So if we look up there, that will be our North Celestial Pole. And it's very close to Polaris. Now, as I said, things will tend to rotate around it in circular orbits that are in a clockwise direction. So I'll try to draw one. And that turned out horrible, but it's pretty close to being centered. So I'm not too unhappy with it. If I can just move it, try to make it better. Well, I can definitely make it bigger. It's clear that I can do that. Okay. Okay, that looks pretty good. So this represents the motions. Correct. Now it moves easily. Okay. This represents the motions of the stars. And you can see that a star, for instance, due east of the North Star, or excuse me, the North Celestial Pole, which again is very close to Polaris, that star will be moving up and to the left. And we also see that a star directly above the North Celestial Pole, and therefore the North Star, will be down to the left. We see that a star to the left of Polaris, or the North Celestial Pole, will be moving down and to the right. And a star directly below Polaris, or the North Celestial Pole, will be moving up and to the right. And of course, we can continue that motion to bigger circles. So if we made a bigger circle, this thing's going to automatically make it something crazy. So I'll try to take off the auto correction. Be something like that again in a counterclockwise fashion. So if you follow this around, you'll see, oh, okay, well, this one's going to do this, and 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 this one's going to do this. And again, we're just following that motion. So we see that stars due east tend to move up and to the right, like this shows, and stars due west tend to move down and to the left, or excuse me, down and to the right. So we now have figured out all those directions that I asked you in these numerous star motion questions. When a star is directly below Polaris, it moves up and to the right. When it's directly above Polaris, it moves up and down and to the left. When it's to the right of Polaris, it moves up and to the left, which you can see right here. You can also see here. You can also see here. So this is a star to the left of Polaris, and this is a star below Polaris, clearly going up and to the right. And if you see a star due east, you expect it to move, whether it be 5 minutes or an hour, you expect it to move up and to the right. And in fact, even if it's 24 hours, because a 24-hour day is a solar day, which is slightly longer than a sidereal day. A sidereal day is a time required for this star right here, say, to go from that spot to exactly that spot again. That's a sidereal day, and that's about 23 hours, 56 minutes. And 56 minutes, roughly. Okay, whereas a solar day is a time for the sun, a very particular star, to travel from a particular spot in our sky to the exact same spot. And that corresponds to 24 hours. Exactly. And that's supposed to be basically a 360.986 degree rotation, whereas this is a 360-degree rotation. So for instance, if I see a star where that arrow points right here, let's do a different color just to make it nice. Okay. If I see a star right here at 8 p.m., it'll be there again at 7:56 p.m. But by 8 p.m. again, it'll have moved to here. So that's why sometimes I'll say, if you see a star at 8 p.m. due east, in which direction or directions will it have moved by 8 p.m. the next day? You'd have to say the exact same thing as if I asked you for 15 minutes later or an hour later. Similarly, if you had a star right here at 8 p.m., it would be back at that spot again at 7:56 p.m. And in fact, we'll have moved down to, say, here by 8 p.m. the next day. So hopefully that helps you a little bit understand how these star motion questions are supposed to be worked out. This diagram, which you can get from just drawing the celestial sphere, helps you. Obviously, the circles aren't great and all that good stuff, but it's still, you just continue those circles on because the entire celestial sphere is acting like a giant crystal that doesn't morph or twist or anything like that. Now, if we turn to the south, I can draw another equator, and this time we'll be looking due south. And I've already hinted at what that's supposed to look like. And it turns out the celestial equator, which I want to draw in, let's say, blue. The celestial equator goes like this and happens to be, happens to be 90 degrees minus your latitude above your south point. And this, of course, is due south. And now if we go on the coast of our beaches, whether it be North Carolina or Virginia, and we look due south, then we know the ocean will be on our left. So this is east over here. And we know that the businesses or sand dunes will be on our right, and that would be our west. You could also think of it this way, that things rise in the east and set in the west. So with that in mind, that suggests this motion should be this way. So if you see an object due south, whether it be Polaris or well, it can't be due Polaris, obviously, but whether it be, you know, Arcturus or some other cool star, then if I ask you at what direction or directions will it move by 9 p.m. instead of 8 p.m., then you'd say, oh, it's moved down and to the right. Similarly, if you see a star west, this gives you the same answer that we got before. It's going to move down and to the right. If you see a star in the east, it's going to be up and to the right. So we see all those questions that we answered before are still there, but now we've got this. And of course, the center of this circle is down below the horizon. So that's why we see a smaller bite of the circle, whereas the center and the circle up top is right above us. And Polaris, say, is something like that. But remember, Polaris is a star too, so it's actually going around in a little circle like that, so close to the North Pole, North Celestial Pole, that it's easy to just assume that's the center because it looks like it. And again, this blue line that I have drawn here is the celestial equator. So that tells us neat things, like, for instance, we know the sun appears to be about 23.5 degrees above the celestial equator during the summer solstice. So if we go 90 minus L, let's say our L is 36 degrees. That's pretty decent. 90 minus 30 would be 60. 90 minus 36 would be 54. So the equator would be, for L equal 36, implies 90 degrees minus L would equal about 54 degrees. But then on or around 6/22, the sun would be at about 54 degrees plus 23.5 degrees, which is equal to, of course, 77.5 degrees approximately. So that's at noon, at local noon, I guess it would be best to say, on 6/22. Similarly, if you had a solar eclipse on that day, the sun would be at a height of 77.5 degrees. Excuse me, the sun and the moon would be at a height of 77.5 degrees. So that's another thing that can help you. So here we've got our sun. Now, if you come back on 9/22, then the sun is at 54 degrees plus 0, because that happens to be the autumnal equinox. In other words, the fall equinox. So it's going to be 54 degrees roughly at noon. If we come back at 12/22, now we're experiencing the winter solstice, and the sun at noon will at this time be about 54 degrees minus 23.4, or excuse me, 23.5 degrees. Now 50 minus 20 is 30, and 54 minus 23 is 31, and 54 minus 33.5 is 30.5. So this will be 30.5 degrees, and that's at noon as well. And then, of course, on or around 322, we're experiencing the vernal equinox, which used to be the beginning of the year. And in that case, the sun would be at 54 degrees again at noon. Again, but with that idea, if we tell you stuff about the moon, like a solar eclipse or a lunar eclipse, you know the sun is actually lining up with the moon, so you can see the moon's at the same spot. You also know that the tilt of the Earth's axis of the celestial, let's say the sun's plane, that appears like the sun's in a plane orbiting us, which we know is not the case, but still, we know that on either side of that, the moon can go about 5 degrees. So the highest the moon will ever be is maybe 77.5 degrees plus 5 degrees. So that'd be like what, 82 degrees, 82.5. And it could be as low as, let's say, 72.5 degrees, because that's about 5 degrees lower. So you can do all sorts of neat stuff like that with this diagram. And you can also, of course, predict, the height of the sun or anything that's lined up with the sun on those certain days. So remember, these solstices is when it's supposed to be eternal, or let's say equinox means equal night and equal day. So that's what happens on that. And then the solstices means the sun stood still. So that's really, really long day for somebody. If you're in the summer solstice in northern on the north half of the earth, then that's the longest day of the year, whereas it's the shortest day of the year if you're down in Australia in the south, which, by the way, Australia is Latin. Australis is Latin for south, just like boreal is Latin for north. So that's kind of some interesting stuff that you can use. But now if you look back there and you say, hey, wait a second, if the sun's going to go, let's say on 622 to 77.5 degrees, well, we know, looking at this, that it's going to rise actually quite a bit north of east. So the sun in this case might actually rise, say, here. And this is on 622. And then it's going to follow this long and high path all the way back here. And it actually is going to come back to this spot, like here. I didn't draw it that well the first time, but the main thing is, if it rises, say, 18 degrees north of east, and it's going to set 18 degrees north of west. But you can see, obviously, on that time of on that type of orbit, which appears to be an orbit anyways, but on that type of path, it's going to be up for a really long time. Whereas if it's south of east, say right here, it's actually going to go up and then come back south of east. And of course, it's not in the sky nearly as long. So that helps us understand why the days are so short in the winter. And it also helps us see that the angle that the earth makes, or that the sun makes with vertical, is quite small on our summer solstice, but quite large on our winter solstice. So this sunlight's actually spread out over a larger area in the winter and a smaller, more intense area in the summer. So there's a lot of stuff that we can get from these little diagrams, just making sense of all this. So let me now show you one more thing, and that's about these questions about the spectra. So the spectra is a big thing that we learn about in astronomy, and basically what we learned from quantum mechanics, and specifically the Bohr model of the atom, is a nice way of thinking about it. Even though we know Bohr's model doesn't exactly work, it's still pretty close. So according to the Bohr model of the atom, you have sort of a nucleus, and then you have orbitals around it. And I'm just going to draw my circles. We don't necessarily, for starters, they're not really orbits, because the particles, the electrons, are not, I did not mean to draw those lips. The electrons are more or less sort of probability densities. They're infinitesimally small, and they have an average distance away that's maybe these radiuses, but in general, they're not really orbiting in any sense based on quantum mechanics. But we do know, as we get higher and higher up, the orbitals get closer and closer together, and the electrons, well, that one didn't come close. The electrons can jump up and down between these levels. So with that in mind, what can happen is you can have a little photon come by. Here's a photon. It's going to come by. and it'll have a certain wavelength. It'll have a certain wavelength or frequency, either one doesn't matter, because E is equal to HF, but it's also HC over lambda. So if that energy happens to match an energy difference between, say, E1 and E2, or between E2 and E3, or between E3 and E4, or between E1 and E5, so on and so forth. If it happens to match one of those energy differences, then the atom can make use of it, and the photon basically disappears. And in its place, if it happened to match E2 minus E1, so I'll say if E2 minus E1 equals HF or HC over lambda, which they're both equal, okay, then the photon disappears. And the /A electron in orbital E1 will jump up to orbital, and I'm saying orbital E2, but it's really the energy of orbital 2 is E2. So what we'd have is an electron would just jump, say, from here to here. If the energy matched E3 minus E1, in principle, so in this case, we're drawing another photon who has a frequency F2 or a wavelength lambda 2, then that photon would disappear and jump all the way up to E3. Like that. Similarly, once it gets there, we're going to find out that it's not comfortable because there's lower states available. We know they're there because this one just left it. So sometime later, that electron will fall back down, say from E2 to E1 or from E3 to E1 or something like that. At that time, another photon will be created and will be sent off in some random direction. And of course, conservation of minimum and conservation of energy and all that stuff's still going to happen. But we basically get the electron falling back down. Now, when those electrons are going up, I'll try to write this as not cursive. When electrons jump up, that, I shouldn't write that. Then photons are being absorbed. I don't know. It's not supposed to be a space in between those words, but it looks like it was. So I apologize for that. Absorbed, which gives us an absorption spectra, which is also a dark line spectra. So this is basically the rainbow with little spots missing. It's a spectrum or several spectra. Okay, so that's why I wrote both of those forms there. So if the electron jumps up, then the photons have to be absorbed, and that's what creates our absorption spectras, which, like I said, looks like a rainbow with little dark lines in it. However, when they fall down, photons are emitted. And that makes an emission spectra. Spectrum slash bright line spectrum. Spectrum. Well, that's a crazy M. I apologize for that writing. So when the electrons fall back down, photons are emitted, and that creates what we call an emission spectra. And wow, that's really some bad looking writing I did there. Let's clean this up a little bit. Make that S look a little better too. Oh, good Lord. So that's emission spectrum. Okay, and that makes a bright line spectrum. In that case, it looks like a, well, if you were actually doing the same atoms and you looked at the spectra one way, you would actually see an emission spectrum. If you looked at it another way, you would see an absorption spectrum. So Kirchoff's laws basically say this: hey, if you're looking at a hot, dense object, and that hot, dense object, for instance, could be the core of a star, it could be a horseshoe stake that you threw in a bonfire, just about anything, you know that they eventually get so hot that they shine red hot. And then if you keep heating them up, they'll go through orange and yellow. And technically they do go through green and blue and indigo, but we don't normally see those colors. We sort of just see it turn from green, or excuse me, from red to orange to yellow to white. And at that point, their radiation is peaking beyond the visible spectrum in what we call the ultraviolet spectrum. So the temperature goes up, which means the wavelength is going down, according to Wien's law, W-E-I-N''S. So if you actually have a hot, dense object like the core of a star, and then you got a low density cooler gas in front of it, what happens is that hot, dense object sends out a complete set of radiation. In other words, it sends out a whole black body slash rainbow. Okay, it's a black body spectrum or a rainbow spectrum. That's one of Kirchoff's laws. A hot, dense object will create a black body spectrum, which is really a complete rainbow. Now, if you see that light being filtered through a lower density cooler gas, say, for instance, like the atmosphere of our sun, or say that radiation may be coming from stars in a nebula, then the nebula, which is the gas around it, will actually suck up all the photons that it can use. And what you'll get is an absorption spectra. In other words, you'll get all that radiation that the star tried to put out, except for the parts that the gas between us and the star could use. Those photons will be sucked up, and that'll leave the black lines in the what would have otherwise been a black body or rainbow spectrum. Again, if you look directly at the star, though, if you would see, again, another type of absorption spectra. In that case, it would just show, because the outer atmosphere, in our case, the photosphere of our sun, absorbs just the photons it can use for its atoms, which are mostly hydrogen and helium, but there's other things in there too. But if you looked at it right outside the core before it ever got to the photosphere, then you just see a complete rainbow. Now, if that light from that hot, dense star shined obviously through its own atmosphere, it's going to lose some of the colors, but then it's going to hit the surrounding gases. Now, if we look at the gases without the star behind it, in other words, the star's like to the right and we're looking at the gas to the left, that gas will have gotten excited from all the radiation going through it. And what we'll see is the emission spectra. This is the third of Kirchoff's laws, the second being the absorption spectra I just mentioned. And this would be basically the light is actually traveling from the hot, dense object, not towards us, but towards our left, say, and that's exciting the gas cloud to the left of the star. That gas cloud is going to send off those photons that are created randomly. It's going to send them off in random directions, and some of those directions are ours. So we'll get what's called a bright line spectrum, which is an emission spectra. Now, if you looked at the emission spectra and the absorption spectra from both those, that cloud with the star behind it and that cloud outside without the star behind it, the black lines would exactly be blanked out by the bright lines in the absorption spectra, because they're all the same elements. So that's how light interacts with matter to some extent. So you can get light coming from a hot dense object, and it'll complete a black body spectrum, which is basically a complete rainbow. And it doesn't just cover the visible spectrum; it goes to the infrared on the low wavelength side, or excuse me, on the high wavelength side, and to the ultraviolet on the low wavelength side, and it goes all the way beyond that. So all the radiation comes from the hot dense object. But if the hot dense object then radiates through a low density cooler gas to get to us, we will see an absorption spectrum, which includes the whole rainbow minus missing black lines. And if it instead goes to the right, say, or to the left, and we look at that cloud without that star behind it, then we're going to see the emission spectra, which is basically nothing except for the bright lines that were stolen from the previous absorption spectra. So that's how light interacts with matter. And then I ask you crazy questions like, okay, these two emissions occurred, or excuse me, these two absorptions occurred. One was in the ultraviolet and one was red. Which transition was red? So red, if you use your electromagnetic spectrum, it's basically great, meaning gamma, excess, meaning X-ray, great excess undermines, meaning ultraviolet, great excess undermines industry. Oh, no, excuse me. Great excess undermines various industries. Marxism rules, okay? That's gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio. And then the visible, of course, breaks out into, in this case, the way I did it, you can see the infrared must be near the red and the violet must be near the violet. So this is Viv-Gior instead of Roy G. Biv. So we get Viv-Gior. So we see red is here. And we see what I say, ultraviolet was the other one. So we also see that ultraviolet is here. Now we know that radio waves are long wavelength, low frequency. They're also low energy. And they're also low temperature. Okay. Whereas this one's long wavelength, this other end's the opposite. Long, excuse me, opposite doofus. Short wavelength. We also see that it is high frequency, high energy, and high temperature. Okay, so if I said these two reactions, one or these two transitions, one was a red photon and the other one was a ultraviolet, then the one with the highest energy would be the ultraviolet, and the one with the highest energy is, of course, is the longest arrow. So the green and another red, okay, that's the photons, then the longest arrow is due to largest energy. Implies UV is green and red is red. So that's how these questions work when I ask you, okay, is this emission spectrum or absorption spectrum? Well, if the arrows point up, it's got to be an absorption spectra. If the arrows point down, it's got to be an emission spectra. And then it's just a matter of figuring out, okay, the shortest to the longest. The shortest should be, of course, the lowest energy. And that means it should be the one farthest to the right in the electromagnetic spectrum, which is great excess undermines various industries, Marxism rules. And then down to the highest energy, which is farthest to the left. So that would be the longest arrow would get the photon farthest to the left, and the shortest arrow would get the photon farthest to the right. And that's how you can slowly pick those out. So those are two of the major questions that come up in astronomy You've seen them over and over again. I've had surprisingly few questions about them, but I see that when you take the test, you don't necessarily do that well on those questions regarding star motion, star being due east, in which way it will have moved at 9 p.m. if it was previously seen at 8 p.m. And also, which photon's red, which photon's mute, which photon's ultraviolet, which photon is yellow, which photon's a microwave, so on and so forth. So hopefully that helps. I'm sorry no one showed up. I will be holding another help session tomorrow or tonight at 5:20, and then tomorrow at 5:20 as well. If you're interested, you need to email me and let me know so I can send you a link. And then I'll be doing it again Wednesday at 5:20, and then again Thursday at 5:20. I might do other times as well, but right now I've got all those set. And if you need me at some time other than the early afternoon, 5:20, or early evening, I should say, let me know and I might be able to set up something and then I'll announce it to everyone. So for instance, if you need to see me around 1 o'clock, I might be able to fit that in, or 12 o'clock, I might be able to fit that in. But right now I'm just assuming most people have work hours they're dealing with, so I'm trying to do them late. So by all means, give me a call, email me, send me a text message, whatever you need. Again, text messages are the most likely to get with me easiest anyways. So send me a text message for best results. Make sure you include your name, what class you're in, whether it be Astronomy 111, PHY 241, PHY 241 night class, PHY 242, PHY 242 night class, so on and so forth. So I'm going to call it. It looks to me like everybody else is not showing up, or no one showing up. So I hope this helps you. I will post it to my YouTube channel and I'll put a link on it. And since I only handled astronomy, I'll put a link on it in AST 111's Moodle course. Have a good day. Bye-bye.